So this lecture is going to be about sort of the general issue that you have. We've been talking about synchronization, and we talked about two very simple synchronization primitives upon which you can build many other much more sophisticated ones. And I wish we had enough time to go through them all, but we just don't. And so what I want to do is talk about a specific issue, and we'll illustrate it with an example, and then we'll show a really novel way of solving it that's actually becoming so widespread that it's really helpful to know about it, and it'll actually, it'll be really neat if you walk into a place to do systems programming and you actually know about this, because a lot of people don't actually know about it. Okay, so yeah, mutual exclusion, blah, 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 we talked about that. There's a lot of examples of shared state in the OS kernel, and often it's managed in linked lists. It isn't always. You may have trees. The Linux scheduler actually uses a tree now. You may have many linked lists, which you sort of move things between if you have a multi-level feedback queue mechanism or something like that. Hashing is also frequent, but hey, if you have a linked list of bins in each hash bucket, then you might end up still with linked lists again. Okay, and the other thing that's really common is that the state is read. It is read a lot more than it's written because the OS needs to look things up and decide what to do. It's not actually modifying it. If it had to write all the time, then the mechanisms we're going to talk about today would actually be pretty annoying. Okay, but there are a lot of examples of shared state. Processes are managed in shared state. File system cache. We'll talk about the last two a lot more when we get into how those things actually are implemented or how you would design them. So anyway, but because we have a situation where we have a lot of things in these simple data structures and they're read a lot, we have some interesting things that we can do. So the question is, how do we implement a linked list that supports concurrent access from multiple kernel control paths, and we expect that we will mostly read it. We will write it much less frequently than we read it. So we have a simple example here. Okay, we have a list node A and B. Who cares what the values are? We really don't care. Presumably they have some meaning. And then we have a pointer to the next node in the list, and we have an anchor to the list that's pointed to with head. Frequently you would also have tail. You'd probably want to have a doubly linked list so you could go backward as well as forward, but we're just trying to distill this down to the simplest version of the problem. Okay? And so we have something like this. The head points to the first node, blah, 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 all the way to the last node has next is 0. Okay? So this is our sort of our context, and we have various operations we might need to perform. We need to look at all the elements. Maybe we need to look up a particular node. We need to find the node with A is 9 or something like that. We need to be able to insert a node into the linked list either at the front or maybe at the back or maybe at some specific position. We need to change the contents of a node. So we're not just destroying it, we're just changing its contents. And then that's all we need to do. We need to remove a node from the list. And I think we all know how to do these things. If you don't, then you probably shouldn't be in CS124. Because that's like really bad. But all of these things are very straightforward to us at this point in our programming careers. But then you take a look at this and say, okay, what about in the context of concurrent access? What about in the context of concurrent manipulation? That's where this starts getting really interesting. And if we didn't do anything about synchronization, we didn't do anything about managing shared access to this thing, it would be pretty quick that our thing would become corrupt. Now, if like 99.9% of the time we only read, then we might not see that corruption right away. We might see it after the system runs for a while. If we had like 60% of the time we read and 40% of the time we write, then we'd probably see the corruption right away. So we have T1 here is our first thread traversing the list. It's got a pointer to a node. Notice it's pointing to the first node. And it's looking for A equals 12, so that's obviously going to be toward the end of the list. And another thread is inserting a node into the list. Okay? So clearly, depending on how we do this, we can run into huge trouble. And part of the reason why we can run into trouble is we could probably specify a sequence of, the sequence of the operations we perform such that threads don't get confused, except that we have reordering at both the compiler level and we have reordering at the processor level. Okay, so several operations. These are going to be our simple example. So new A is 51, new B is 24, next is P next. So we just go ahead and say, you're going to slot in after Yeah, after the node that T2's P value points to, and then P arrow next equals new. So we go ahead and stitch it in there. And we can try to do this in a way, you can see that the order that I have it probably is the most reasonable order, right? So P arrow next doesn't actually change until we're all hooked up and ready to go. You can imagine if we had some other order where we said, P arrow next gets moved up ahead of some of these other operations, somebody might see an uninitialized node. Or if we have a situation where the write to P arrow next isn't atomic for some reason, which thankfully is not a real consideration on IA32 or x86-64, that will generally be atomic. Okay, so there's various things that we could run into, but the fact that we have a compiler that reorders instructions and a processor that reorders instructions basically means we're in trouble. This will eventually fail. Okay? Yeah, and you could also throw in other considerations, which we don't really talk about because we don't have a compilers class yet, but you can imagine also in the context of caching values in registers, if I did other things to P arrow next before, or I looked at it or something like that, before I went ahead and exited my function or something like that, I may have a register, I may perform that write to the register, and then later write that to P arrow next as a memory access. So, even caching stuff in registers can interfere sometimes with these operations. Okay, so these are the operations the writer thread performs, and we say they form a critical section because we need to make sure they all happen atomically. And if they're going to happen atomically, then we need to make sure that that thread has exclusive access to, well, probably at least P, the node that's pointed to by P, but we need to some way exclude other threads from looking at this state while we manipulate it. So that's kind of the challenge that we have here. So what's a really simple way of solving this problem? Okay, how do we avoid concurrency bugs? Well, you could get really clever and sophisticated and say, well, last time you talked about fences, and you could probably use a fence somewhere and actually force those operations to complete, and that would be a good choice. We'll actually talk about some of those things today. But if we were really naive and we use sort of the traditional sort of early approach to these kinds of problems, we would go ahead and add a lock. If you want to do anything to this list, you have to acquire the lock first. And notice that I said any thread on the slide. So if I want to read the list, I have to acquire the lock. If I want to change the list, I have to acquire the lock. And so we'd have to think carefully, is this thing actually accessed from interrupt context? And if it is, then I have to make sure I disable interrupts before I acquire the lock so that no interrupt handler can ever access it. And inside of an interrupt handler, it should be fine. It will have exclusive access because, again, you think, what can interrupt what? If I disable interrupts before I access this thing, then if I'm in the interrupt handler, I know nobody else is accessing it. Okay, so those are the kinds of fun things that you see when you implement operating systems. And I talk a little bit about multi-core systems. You can think about that as well, because remember, I may have other processors accessing this thing. If I do, then I probably need spin locks as well. So a few things like that. Okay, so the first question that you should ask yourself, and again, you may not be used to asking these kinds of questions yet, but you should get used to asking these questions really quickly because it'll, it's part of being a badass programmer. Why must readers also acquire the lock? They're just reading it. You know that they're not changing it. But given the way that we've designed this system so far, the only way that the readers will know that the writer is not writing is if they also acquire the lock. So this lock mechanism becomes a communication mechanism or a coordination mechanism between all the threads. The readers have to acquire the lock because the writer acquires the lock, and that's the only way that we can actually ensure mutual exclusion. Okay? So you can see that in a sense, the readers don't have to acquire the lock, but that doesn't mean our system is correct anymore. Right? So this is sort of, everybody cooperates by making sure they acquire the lock before they manipulate the shared data structure. And if they don't acquire the lock, we have a problem. Okay? So it's sort of voluntary collaboration here. Okay, so obvious issue with this approach. There's actually a couple of obvious issues with it. The first one is that readers should not block other readers because we know that readers don't destructively change the state. So why should readers actually change things? Okay, and remember the context is we expect this data structure is going to be read the vast majority of the time. We're not actually going to write to it most of the time. We manipulate it very infrequently. Okay? And it is okay if the writer holds exclusive access while it writes to this thing. Or at least we're saying that this is better than the old solution. But it's not great, and we'll talk about much better solutions to this as well. So we're saying that writers will accept it if they hold exclusive access to the list while they're modifying it. And so what we say is that this solution, as we have it here, a single lock guarding both reads and writes, making no distinction between readers and writers, has very high lock contention. Lock contention just means people spend more time waiting for the lock. I shouldn't say more time than. They spend a lot of time waiting for the lock. Okay? So that's what we mean when we say there's high lock contention. We have a lot of situations where threads are waiting to acquire the lock as opposed to doing real work. Yes?
Wait, what if you just check if the lock is taken?
Yeah, you could have a situation like that. If we had a lock where we could try to acquire it and we actually had other things we could go do, oh, I couldn't get the lock, I'll go do something else, then that would definitely reduce the lock contention, because you're spending a lot less time waiting for the lock. But if you have a situation where the thread must acquire the lock before it can do its next thing, which is usually the case, because usually we keep these kernel threads very simple in their sequence of operations. If it has to acquire the lock before it can do anything else, then you'll see the high lock contention again. And remember that we're expecting there to be a lot of reads, and so if we have a lot of reads, everybody's got to acquire the lock, and that's lame. Okay. So that is the concept of lock contention. So we'd like readers to not block readers, and we will accept for now that the writers will block everybody. But there's a simple mechanism for this. We actually mentioned it in passing last lecture. Does anybody know what we could use to allow readers to not block readers? Yeah, read-write lock. It's right in the name, right? You could be more fancy pants and say a shared exclusive lock and say, oh yeah, readers acquire the shared lock and writers acquire the exclusive lock. You could do that as well. It's the same thing. But now we can basically allow readers to overlap readers, but writers still acquire an exclusive lock. And obviously there's all kinds of considerations. We typically touch on some of these things in CS24 exams because we don't have time to talk about it in class. Yay. So, you have a lock where you allow multiple readers to acquire the lock at the same time. If a writer wants to acquire the lock and there is one or more reader, then the writer is not allowed to acquire the lock yet until they're all finished, and then the writer gets a lock. And you have, fairness issues. Should you allow people to hop lines? Things like that. You can definitely have readers get starved or writers get starved in certain circumstances unless you are really careful in how you design it. Okay, so we change to read-write lock, T, list lock. So we have something like that now. And there will be two lock request operations. We can still have only the one unlock operation because the lock can remember who is holding it right now. So you have either read lock, which means other people can also call read lock and get the lock granted, or we call write lock, and that will only be granted if nobody else is accessing it, and nobody else is allowed to receive a read lock or a write lock as long as I'm in my write lock. Okay? So this is kind of the approach. Pretty straightforward. And you can see that we're basically reducing lock contention. Readers don't have to wait nearly as long as they used to because now we allow multiple readers to overlap, especially since we know that we're going to have a lot of readers. And so you can see that, like I say here, we increase concurrency. So you can think of it lock contention. The more lock contention you have, the less concurrency you have. The more concurrency you have, the less lock contention you have. Okay? So a few annoying issues. Readers still acquire a lock. You may not really realize that that's an issue. But you start to realize it when you try to build highly scalable systems where you have a lot of these kinds of locks. Okay? There's a little bit of overhead just accessing the lock. I say I want to read lock this thing. Okay, that's fine. Give me your 100 or so clocks that you have to pay to acquire this lock. Okay? That's the minimum tax. Okay? So, and a write lock, same thing. So we basically still have an overhead for lock acquisition. And like I say here, the term is generally, this is usually described as lock overhead. So what is the overhead for acquiring the lock, for releasing the lock? Remember, when I release the lock, if somebody is blocked on the lock, then I need to go wake them up. So then I have to move them from a blocked queue onto the ready queue. That takes a little bit of time as well. I'm touching memory, blah, blah, blah. So you can see that there's a little bit of overhead for this synchronization mechanism. It is not free. And writers still block everybody. Which, if you think about it, why do I lock the entire list if I'm doing something maybe only to the end of it? Or maybe I'm only doing something to this node. If I have, let's say, 45 nodes in my linked list, and I want to change one of them, or insert one of them, or replace one of them, why do I lock the entire list? So what might be an approach for solving that, to make it so that writers don't necessarily block everybody? What might we do? This is not rocket science. There's a pretty obvious answer. Yeah, I could do something like a read-write lock per node, some option like that. So what happens, if I have a read-write lock per node, what happens to my lock contention? Does it go up or down? It should go down, right? The reason why is because each lock will guard less. Right now, we guard everything with one lock. But if each lock guards a lot less of the data structure, and that's what I'm coordinating access on, then I should actually see lock contention go down, unless I have some stupid situation where I only ever add stuff to the beginning, only ever remove stuff from the end, or some situation where the access pattern basically means that most of the time I don't actually require write locks throughout the list. So you could have access patterns that don't really play well. But in general, you should expect the lock contention to go down. We call that lock granularity. What is the size of the thing that I'm locking? If I just decrease the size of the stuff that each lock is guarding, then I'm increasing my granularity. I need more locks. Now, what happens to lock overhead? It goes up a lot, especially if I had this approach where instead of having, if I have 45 nodes in my list and I want to traverse the list, now I have to acquire 45 read locks. That's pretty lame. Before I only acquired one. Okay, so you can see that, so this is what I just talked about. So we have more locks, each governing a smaller region of data. And it's interesting because you start having other challenges that start to emerge when you do this stuff. Because if I lock the node and I want to change its next pointer, well, do I need to lock the next node as well? What all do I need to lock to make sure that I do these updates correctly? So there's a lot of interesting new challenges that start to emerge. Let me see. Threads must acquire many more locks, so we talked about that. Writers can only lock the parts of the list they're changing, so we get reduced contention in the context of writes. Okay, I can read all the way up to where the writer is writing, and then I just wait for the writer to finish, and then I can continue reading the list after that. Okay, so I have something like this, a read-write lock in each node, and of course I actually still need one more read-write lock to govern the head pointer, because I could change the head pointer as well. So, like I said, there's a few other details here that we need to include, but we're not going to talk about them. All right, so anybody have any questions about this approach in general? Because what I'm going to do now is skip. This lecture has 60 slides. There's no way we're getting through it all if I don't skip a big chunk of it. The part that we're going to skip talks about a lot of little attendant details, like I just mentioned. You start needing to do, this mechanism called crabbing. You know how crabs sort of walk side to side? Well, the same thing when you have fine-grained locks in a data structure. You have to lock something, and then you own it. And if you want to do something to the next one, you have to lock it, and then you can release your current lock. So they call that crabbing, where you're sort of guarding each thing that you're stepping from as well as the thing that you're stepping to. You can read all about it. What we're going to do is start talking about the fact that this is kind of just a generally difficult approach. I'm not actually seeing any updates. Did my computer just lock up? Okay, here's what we do. I don't know why that was. Okay, so yeah, lock-based approach has a lot of issues. Okay, you have this big trade-off between how many locks do I have. The more locks I have, the more concurrency I frequently get, the less lock contention I have. But the higher lock overhead I pay. So the bigger the fee. Okay? If I have one lock or just a few locks, then I have a really low lock overhead, but I have really huge contention issues. No good, no bueno. So what do? Basically, locks have a lot of downsides. And so the real issue that we have here is we're trying to prevent different threads from seeing inconsistent state. That's really, so you take a step back. Our issue is not everybody must lock stuff before we manipulate shared state. The real issue is that we have this state that may be inconsistent. We just want to make sure people don't see inconsistent state. Okay? And like I say, the big issue with our specific example is that we can't really guarantee the order of these operations, how they'll be performed by one thread. Why do we care about that? Well, we really only care about it because multiple threads doing this concurrently may have interleavings that are invalid, where a thread is able to see incomplete state or inconsistent state because the other thread hasn't finished doing something but it's become visible. Okay? So, like I say, locks are helpful only in that they guard all the state changes so that we don't have to worry about ordering issues. That's why we like locks, right? Because I manipulate things and I guard my change so that nobody can see it until the manipulation is complete. So you have situations like that. Okay? So what if we could actually impose a more intelligent ordering? And I hope you're starting to think, okay, fences, he's going to talk about fences. Well, it turns out that we actually don't need too much sophistication for doing this stuff. Okay, so T2 inserts a node. So first step, prepare the node. Okay? So, and I wanted to mention, I just finished, like at the end of last lecture, very hastily telling you that kernels don't really have allocators like applications do. And then in this lecture, I'm using malloc and free. Frequently there's calloc, like kalloc, not calloc, and or kmalloc, things like that for actually allocating memory in the kernel. We'll talk about how those allocators work in a few lectures, but we're just simplifying the presentation of the problem. So use your imagination. Those are kernel allocation calls if necessary, and so forth. So we're just trying to illustrate the nature of the issue. Okay, so we prepare a new node. We don't insert it into the list yet. And you can see that new A, new B, new next, those things could happen in any order. We do not care. Okay? Obviously, the first operation should complete before any of the other ones do. If that doesn't happen, then you kind of have real issues. But we can presume that the last three operations can occur in any order because they're not visible yet. Okay? And you can see that T1, so T2 is the one manipulating the list. T1 can just go on. It doesn't care because it doesn't see the changes. They're not even visible. If it follows next, it doesn't see the new node because it isn't actually in the linked list yet. So then step 2 is that we want to atomically change P arrow next to be new from being what it was before. And when we say atomically, we mean so that T1 sees it either as the old value or as the new value. Obviously not some amalgam, because that would also be horrible. Okay? And like I say here, if the CPU can perform that single word write atomically, then threads fall into camps now. They either see the old version of the linked list or they see the new version of the linked list. They can't see some weird mangled version. Okay? So we do this. That has to be a single atomic operation. And so the result is that readers never see an invalid state of the list. Okay, so that's all okay, that seems simple, but we could do this with fences. Who cares? What's the big deal? Why are we making such a big deal out of this? Well, it turns out it's a little bit more complicated than this. So the mechanism, as fully developed, and we're going to go through most of the general nuances of it today. So it's called read, copy, update, and you've probably heard of it. Who's heard of RCU before this lecture? Before this class? Okay, wow, this is really cool because this is actually becoming one of the more common synchronization mechanisms within Linux and is becoming more and more widely used. So it is the wave of the future, the wave of the present, and it basically is a lock-free approach to managing shared state. You may have heard of this term as well, lock-free. What we mean is let's orchestrate our operations between multiple concurrently executing threads in such a way that we don't ever need to acquire locks. And I tell you, it's way faster, and it's way more scalable with the number of CPUs. I have some charts I'll show you toward the end, where lock-free approaches are actually really powerful in achieving very high concurrency without hardly any lock overhead. Okay, so all changes to shared data structures made in such a way that the concurrent readers never see the intermediate state. They only see either the old version or the new version. And remember, I said there's an atomic change. And so you can divide people into two categories. You either see the old version or you see the new version. And the changes are broken into two phases. This is where the term read, copy, update comes from, because you have readers, and then you, if you want to write, then you do a copy and then an update. Okay, so you make a copy of the specific parts of the data structure that will be the new version, and you can do whatever you want in whatever state you want, in whatever order you want. Who cares? So that's the copy part. And then once you have perfectly crystallized, ready state to expose to the rest of the world, then you do a single atomic operation. That's your update. And that exposes the changes to other readers. Okay. And virtually always in read, copy, update, and also I should say in a lot of other lock-free data structures, I should say, because you can also have atomic data types, where you're not manipulating a pointer. But generally in lock-free data structures and in read, copy, update in particular, this atomic operation is always changing a pointer. Okay? It's pointing from one valid version of the shared state to another valid version of the shared state. And since it's atomic, again, people either see the old version or the new version, but they don't see something gross. The way that it's generally described is that this change is a publication of the new version of the value. So, like I say here, it generally is described as publish subscribe. So we prepare something for publication just like you would at a newspaper or a magazine. I know people are like, what are those things? Pretty soon that's going to be the way to, oh, it's just on the internet. So, but anyway, once you have it all prepared, then you publish it by changing the pointer. And so you have to make sure that all the initialization is completed. And that's really easy to do. We just enforce a memory barrier. Okay? And since it hasn't been published yet, we can get away with just using a write memory barrier. Okay? And like I say here, of course, you need to make sure the compiler imposes an optimization barrier. That's really easy. Remember, that was like no assembly code. We just tell the compiler to stop pretending that that value is cached anywhere. Okay, so we can implement it like this. Oh, and it looks like I need to work on my font, so I apologize for that. Atomically publish a value v to pointer p. Okay, so we have this magical function, which is actually a macro called RCU assign pointer, which atomically assigns v to p. And so you can see we have a write memory barrier if we're on a multiprocessing system. If we don't have if we don't have a multiprocessing system, that thing turns into nothing, and we just perform the operation. Okay. And the reason why is because IA32 and x86-64 really love programmers. As long as these operations are word aligned, it's already atomic, even in multiprocessor systems. So we don't actually have to worry about doing anything extra. We just perform the write, and that thing is automatically going to be atomic. Go us, that's simple. So this is the way that T2 would now update the linked list. Notice we do all of our stuff. That's the initialization, setup, blah, blah, blah. And then we call RCU assign pointer. That publishes the new node. And it turns into that code up there, which, you know, is really cheap, right? So what is our locking overhead? Well, I mean, it's not really locking anymore. So what's our overhead of RCU? Well, it's really cheap so far. So that's publishing. Now T1 needs to see whatever the current state is. Now do we care what the current state is? Not really, and you'll notice that this doesn't have necessarily the same consistency guarantees as databases do. We'll talk about that toward the end. But T1 just needs to see whatever the current state of the pointer is, and again, it needs to do that atomically, so it needs to either see the old value or the new value, and it shouldn't see anything intermediate. So this is what we had. We had T1 looking for a node with a specific value of A. So we get the head pointer, We start with b being -1 because let's say we're retrieving b out of the node with a specific a, and we say if p arrow a is the value, then we pull out the b and break out of our loop. Otherwise, we'd go to the next node. Okay, so where do we care about? Well, we care about list node star p equals head. That needs to get a value that may be manipulated through RCU. And p equals p arrow next is a value that may also be manipulated via this read copy update mechanism. So we say that T1 is subscribing to the value of the pointer. Okay, publish, subscribe. So pointers change, we say it's a publication. Somebody reads the pointer value, it's a subscription. Okay. So we need to make sure that P arrow next is read before anything else happens. This sounds crazy, right? Seriously, you want to read P arrow next before any accesses to P arrow A or P arrow B. So we're saying that that P equals P arrow next needs to finish before the rest of the loop that comes after it in execution, right? Well, the reason why we need to care about this is because there are a few processors, cough, dec, alpha, cough, where this can actually happen. It will actually schedule the P arrow A or the P arrow B to occur before P is updated to point to the node it's supposed to point to. Okay? Now, is that actually what happens in reality? No, the real issue is that you have these two data caches in the DEC alpha processor that are not kept coordinated with each other. And so you could have the old value of P read from 1 to handle the A access or the B access, and the new value of P is in the other data cache, and they aren't coordinated. Okay, that's the real way that it happens. But in this situation, IA32 already ensures that reads occur in a reasonable order. So P equals P arrow next will always happen before we get to the next iteration of the loop and read out P arrow A and P arrow B. Okay, so thankfully this is a norm. Yes, question? Yes, so the issue here is you can't really release things until you've coordinated with everyone else. You're jumping ahead of the story. This is good because you're thinking about the implications of what we're talking about. But yeah, we'll actually address that issue. It is surprisingly complex, so we'll definitely address that. Yeah. Okay, so this is probably not worth mentioning, except that you do need to think about it on processors other than IA32. IA32 is, like I said, really nice to programmers, at least when it comes to concurrency. Okay, so we encapsulate subscribe in a macro. Okay. Again, what do we mean by subscribe? I'm reading the value of a pointer. Okay, well, like I say here, we call it RCU dereference. Again, you have SMP read barrier depends, which if you're not on a multiprocessing machine, or a multi-core machine is really how I should say it, then that turns into nothing. If you're on a machine where reads are ordered all the time, then it turns into nothing. If you're on a DEC alpha, then it turns into a read fence. Okay? Because you have to make sure that the reads finish before this read occurs. Okay? So what do we do? Type of P underscore value equals access once. What does that mean? Okay. Access once is a macro that ensures that you actually read it. Like the compiler can't just trust that the value's in a register. It has to read it from memory. Okay? I don't think I have a definition here of access once. Yeah. So the definition of access once is cast it into a volatile version of the same type, and then read it. When you cast it into a volatile version, you're telling the compiler, this thing may change, and I don't know who might change it, but it may change, so you better read it. Okay? So access once emits no additional instructions. It just makes sure that we read it from memory as opposed to reading it from a register. So it may be slightly slower, but it's not significantly costlier. And then we just return the value that we read. Okay? That's all we do. Okay? So subscribing is cheap, and publishing is cheap. This is really looking nice. This is looking like a fantastic approach. Okay? So this is the updated version of our T1 code. We RCU dereference the head because, hey, we're subscribing to it. And then P equals RCU dereference P arrow next. And that's how we get to the next node. Okay? So far, this is looking pretty cool. Okay, yeah, like I said, the cost is shifted onto the writers because they may have to do extra stuff, because instead of just changing things in place, that's obviously the cheapest way of doing it. Instead of just creating it in place, now I have to make a copy and mutate the copy and then publish the copy, and then clearly I have some garbage that I have to clean up. So the writer has to do extra work, but we're presuming that this writing is going to happen very infrequently. And writers aren't blocking anybody anymore. They can go ahead and do things on the side all by themselves. Okay? Now again, the observant student will be asking the question, well, yeah, but there's also another issue of what if two writers are trying to write to the same thing? Let's say we have two writers trying to write to the very same node at the same time. They both create copies. They both want to publish. Now you lose a node. Well, that's a very good question. We won't talk about how to deal with that. I wish I could tell you all about lock-free data structures. Mike and I actually were kicking around the idea. There's this book, 7 Concurrency Models in 7 Weeks, which I love. It's a great book. The person is clearly more in the functional programming vein, which there's nothing wrong with that, but it constrains what kinds of concurrency models that they look at. And Mike and I have talked longingly about having a CS11 concurrency track or teaching a class on different concurrency models and taking people through all the different approaches, because there's some really clever stuff, and you guys should know it, but that probably won't happen anytime soon. So we dream. Okay, so yeah, readers incur 0 overhead. Writers incur low overhead. Now, like I said, writing occurs infrequently, but it still costs more than it did before. Okay? So we're sort of expecting that we've basically thrown away all the lock contention, or not lock contention, we've thrown away all the lock overhead of acquiring and releasing locks. We're actually losing all of our lock contention as well. Presumably that is a much larger benefit than the new cost that we're now incurring on writes, taking more effort. Okay? So that's the idea, that's the premise, is that this is actually going to be overall much less costly. It turns out in practice it totally is. But even though writers are more expensive, it's I should say the specific modification of state is more expensive. The savings overall is incredibly huge. Okay, so we want to modify a list node. So you see now P is pointing at the second node. And we've used RCU dereference to navigate to P and so forth. We can't change it in place. We have to make a copy. So notice we allocate a new node. We set what A and B should be. And we go ahead and, so what are we doing here? We're saying that B is set to 15. So yeah, we have to create a new version where, I think this is actually a bug in my slide because the new node doesn't actually have B as 15. Our kernel is buggy now, so I'll have to make sure to update that. But you can see that this is the idea. I want to modify a node, then I have to create a copy and change the value, which I failed to do, and then use RCU assign pointer to do that. Okay. And so, like I said before, this means that readers basically fall into one of two categories. Either they saw the old value of prev arrow next, and they saw the old version of the node, or they see the new value of p arrow next, and now they see the new version of the node. Okay? Not on my slide because they're the same, but in concept, that's what they would be seeing. So the upshot is that all readers see a valid version of the state. So we don't have inconsistent state anymore, but we do have the fact that some readers might see an old version and some readers might see a new version. If we're insensitive to that kind of issue, then we're fine. Okay, so are we finished? And this is where we start talking about releasing resources. I created a new copy, changed its values, published it, and now I have the old version. P is pointing to the old version, right? So I need to add in some operation to release that memory, or else my kernel will quickly crash because I'll run out of space, right? So I have a free P. What's the issue with this? Yeah, there might be a lot of readers, in fact. You know, you could have situations where you might have quite a few readers. If you look for one node and then you need to change something 15 nodes down, and so you go to it and you start to change it and you want to do things like that, you might have a lot of readers that are actually affected by it. So the obvious issue is that if somebody's following the old version of prev arrow next, they may be using the old node when the free is called. So really, all the complexity of read, copy, update centers around this issue. When can I free stuff? That's really what all the complexity of read, copy, update comes from. Okay, so we have to make sure that the data is only freed after all the people who were observing it have finished with it. And so how do we actually tell now the readers have finished what they were doing? That's the big question when it comes to read, copy, update. Because remember, we don't really have very much that we're doing to synchronize access to these data structures. People are sort of doing their publish subscribe thing, but that's it. They haven't really said, hey, I'm in this node, because we don't like having to do that. So we have a new sort of semantic rule that we apply. And we define it in this term, a read side critical section. What we basically say is that when we start reading this data structure, or I subscribe to some value, I enter what we call a read side critical section. Okay? When I'm finished using that pointer, I leave the read side critical section. And there is, okay, so we haven't gotten to the rule yet, but this is how we denote them. We have RCU read lock. Okay, do we actually have a lock? No, you'll see how easy this is to implement. RCU read unlock. Okay, we end the read side critical section. Okay, so this sort of denotes the space that we're actually in the read side critical section. So since our thread is just traversing the list looking for a particular node, we go ahead and just surround the entire thing in a read side critical section. I read P, I go ahead and look at P, and I continue to look at P, and then I get P arrow next, so why don't I just throw the entire thing into a read side critical section? If I had situations where I finished using P, maybe I pull out P arrow next or something like that, I suppose you could break this into multiple read side critical sections, but in this case, I kind of can't. I have to have the whole thing in a single read side critical section. Okay. Here's the rule. It really is this simple. It's funny because instead of using locks, we're training programmers, which is arguably more complicated. But this is why it's such a complex concept, is because you have to get programmers to think differently about concurrency. So the constraint on read side critical sections is that you are not going to ever allow readers to block or sleep inside of that read side critical section. That's the rule. Okay? So internalize that fact. It turns out that people have come up with other versions of RCU that relax this constraint, but the original RCU implementation said if you're subscribing to pointers, you're not allowed to block, you're not allowed to sleep, which means you're not allowed to be preempted. That's kind of really important detail as well. Okay? So I'm inside a read side critical section. I have to be able to progress until I finish. Now I can be blocked. Now I can block. Now I can do whatever. Somebody can put me to sleep. Okay? T1 follows this constraint. It makes no system calls. It doesn't it doesn't acquire any locks. We could try lock if we wanted to, but we can't lock with a blocking lock call. Okay? So you can see in here, we're going to progress until we're finished and we leave the read side critical section. Okay? Yes? So what if a timer interrupt comes in? We're not allowed to interrupt this code. So that kind of indicates what we might do inside of RCU read lock. Maybe we have to disable interrupts. And inside RCU read unlock, we re-enable interrupts. We're not allowed to be preempted. That's the rule of RCU. So RCU read lock makes sure that we cannot be preempted. This is not inside user code. This is inside kernel code. Yeah. We're not, we haven't even started talking about user land yet. We're still inside the kernel. So yes, we're allowed to do this. We disable interrupts, we do our thing so nobody's allowed to preempt us, and then we unlock at the end. Okay? Alright, so yes, we use read side critical sections to define when old data may be reclaimed, because if you think about it, we have all these readers doing their magic, accessing data structures, playing along, not stepping on each other because they're just reading. And you can see that each reader's arrow starts with a call to RCU read lock, and the arrow ends where they call RCU read unlock. So this is their extent. Yes?
So doing this, you'll like almost never have interrupts on.
Doing this, you almost never have interrupts on. Well, that's not actually true because there's other ways to prevent preemption. So we'll talk about that in a second. The other thing, too, is that you really only have this issue if the interrupt handler also wants to manipulate the shared data structure. If the interrupt handler is doing something completely unrelated, you can let it preempt, and that's perfectly fine. As long as it doesn't kick that reader away from completing their read side critical section. Because remember, interrupts have to execute till completion. That's fine. They do it. They return back to the code that was interrupted. The reader continues until completion, and then the reader can be preempted. So really, not having interrupts is only about if we have the same shared data structure, the interrupt handler can dispatch away from that kernel thread. Okay? And so we just make sure that that's not allowed. Okay? We'll talk about that briefly because we don't have a lot of time. Okay, so we have RCU assign pointer. That's where we replace the old version. And so you can see here that we have readers now in two groups. Where does the group start? Well, if RCU assign pointer is on the right of the start of the arrow, then I'm in the old group. And if it's on the left of the start of my arrow, then I'm in the new group. Okay? And since it's atomic, no reader's arrow is allowed to start on that line. They either have to start before or they have to start after. They're not allowed to start on the line. Okay? So what readers might see the old version, I'll just go ahead and throw this up here. So RCU read lock falls before the writer calls RCU assign pointer. When can the writer reclaim the old version of the data? Just looking at the picture conceptually, when can the writer reclaim the old version of the data? If your arrow starts before the line, you look at whose arrow is the longest. When that arrow ends, that's when you're allowed to reclaim the data. Does that make sense? Okay. So when all the readers who saw the old version have called read or RCU read unlock, then you know that you can go ahead and reclaim the data. Okay. So we call this, and so this is the earliest. We can reclaim it even later. That's perfectly fine. It won't be perfect resource management, but we could even wait longer if we wanted to. But we can't go any sooner than that line. Okay. So we call that the grace period. The period where we're letting readers get their act together and get out of the data structure. Okay? Now, it's not really like they better hurry up and do it. The writer has to wait until the readers are done. Okay? So the writer has to figure out when that grace period is over. And it doesn't have to be precise, but it does have to be accurate. It can't be shorter, sooner than the grace period must end, or can end, but it can be longer if it wants to. So again, we have this operation, synchronize RCU, which encapsulate this. And so the writer does something like this. Okay, we allocate our thing, we publish the pointer with RCU assign pointer, and then we call synchronize RCU because we need to free stuff. After synchronize RCU returns, okay, so synchronize RCU blocks until all the readers are finished, then we free the old thing. Okay, so we go ahead and replace or add synchronize RCU to our diagram. Okay, so how does this actually work? This is the interesting part of read copy update. Readers are not allowed to sleep or block. Okay, they must progress until they call RCU unlock. Okay, to end their read site critical section. So here's a question. How many readers are allowed to be executing at any given time? If I switch away from a reader and it gets preempted, it can't be inside of its read site critical section. I'm not allowed to do that, right? Just one. Is that how many CPUs are on the system? What if I have 4 CPUs? How many readers can be active? Yeah, 4. So basically, I can only have the number of readers. I should say the maximum number of readers is the number of CPUs on my system, right? Otherwise, if there was one more than that, then I would have had to context switch away from it and it would be blocked. So that's not allowed. That's the constraint. We're not allowed to switch away from a reader until it finishes its read side critical section. Like I say, if the reader's inside its read side critical section, it has to occupy a CPU. Okay, so we also, like I say, require the OS can't preempt a kernel thread that's inside of a read side critical section. Okay. So basically, we disable kernel preemption in these contexts. That's just basically what we were saying before. Now, what does this really mean? We already talked about preemptible kernels versus non-preemptible kernels. Not being able to preempt is not the end of the world for multitasking. Hopefully you all remember this. Hopefully you guys got that. All we do is basically fall back on scheduled context switches. We finish the read side critical section, and then we context switch after we end it. Okay? It's not like it's the end of the world. We just can't context switch right now. Okay? So the CPU executes a context switch. Then we know the kernel thread must be outside of its read side critical section, which means it's ended. Okay? So we can actually exploit this. We just have to make sure that there's at least one context switch per CPU, and then we know we're done. Okay? And like I say, that may not be a perfect bound, but it is an upper bound that includes the grace period. And so that's what we do. Which is weird, but we just watch to make sure that everybody has done at least one context switch, and then we're finished. Okay? This is the simple, naive approach. Synchronize RCU. Well, I'm going to enumerate all the CPUs in the system. I'm going to switch my writer thread to each one of those CPUs in sequence. And then I know Synchronize RCU is complete. Okay? Where run on might simply say, I'd like to set my processor affinity to whatever CPU's value is, and then I yield. And the next time I wake up, I'll be on that processor. Okay? And then I set it to be the next processor, and then I yield. And then I wake up on that processor. So Synchronize RCU is just hopping from core to core. And once it's made its trip through all the cores, then it knows that there's been a context switch on every core. Now, are there faster ways of doing this? Definitely. Real RCU implementations don't do this, but it's nice to know that there's a really simple implementation that can actually do this. Okay? And of course, once you have a context switch on each processor, you know that you are out of all the read side critical sections of the readers that started before Synchronize RCU was called. Or actually, it's the publish, the RCU assigned pointer. Okay? So, single processor system. If I'm in a writer, all the read side critical sections that came before I write are done. Because if they weren't, then I would not be running right now. Okay? So Synchronize RCU turns into a no-op, which is crazy. Okay? Okay, so we're not going to spend very much time talking about that. If I'm on a multi-core system, then it's a little bit more complicated, but like I said, there's definitely been optimizations to that approach, so we won't talk about that. You can read about it. Read lock and read unlock, also simple. Synchronize CPU uses context switches. Okay? So they don't actually have to do any bookkeeping. If you're on a multi-core system with kernel preemption, this is what I was saying before. You're inside of a kernel thread. You need to make sure it can't be preempted inside that read side critical section. So you just disable preemption. You fall back on scheduled context switches. It's not the end of the world. Okay? So preempt disable, this would be like the Linuxy version, would just up the preempt count so that it can't be preempted. And then preempt enable would just decrement the preempt count. Okay? So yeah, single processor system with an OS that doesn't allow kernel preemption. Read lock and read unlock don't do anything because preemption is already not possible. Okay, again, kernel preemption. We still have multitasking. So read lock and read unlock become super simple. So I actually show you a single slide in a second. Let me go ahead and just dive through this last part. RCU is awesome, but it is just as much about training programmers to think differently as it is about coming up with a technical solution. Because you'll notice, okay, I've got to wrap stuff here. The real key is readers aren't allowed to block. That's the key there. And then all this other magic actually works. So like I said, there's as much about training programmers as there is about actual synchronization. Okay, like I say, no lock, so you have basically no lock overhead. The implementation, at least a naive implementation, is super simple. And most of the time, especially on a good processor like the Intel processor, super fast. This is the entire implementation. Okay, and this has support for kernel preemption and multi-core. Crazy, right? If you're doing this for a single core operating system without kernel preemption, then read lock and read unlock become nothing. Synchronized RCU becomes nothing. And obviously all the SMP operations drop out. And you have your entire RCU implementation. Okay? It's basically no code. And it's all about training people, really. So it is only useful in specific circumstances. Like I say, there are many more readers than writers. Consistency, like in terms of database consistency, must not be a strong requirement, or else you're going to be sad, because you can definitely have threads seeing old and new state in ways that are not very well defined. And so if you don't have these constraints, then RCU isn't your solution. Okay, but thankfully, there's a lot of parts of, it's probably scary, but there's a lot of parts of operating systems that don't actually have strong conditions here. Okay, let me show you really quickly, and then I'll let you go. RCU use in Linux, skyrocketing. The kernel is using it more and more and more, and it's getting faster and faster and faster. This is the other one that I really like to show, where up and to the right is not always good in computer science. It's really good in business. But in this case, you can see RCU versus read-write lock overhead as the number of CPUs increases. And so you can see how much read-write locks slow down as you increase the number of CPUs, and the coordination costs go up. RCU basically remains flat. Okay, really great. Now the rest of this stuff, this talks about various versions of RCU that suck less, and you start getting some really powerful mechanisms, because you can support both blocking and preemption in some of the more advanced versions. And Paul McKenney is basically the guru on read copy update, because he kind of invented it and talks a lot about it. So he has a lot of details about it. And you can read. Oh, and there's even user versions if you want to actually do this in user space, which is crazy. Okay? So any questions? All right, I hope you enjoyed that. Next time we'll talk about something that's actually necessary, but this is really cool. And so I wanted to make sure you guys saw it. So I'll see you all next time.